Okay, section 6.9, electron configurations and the periodic table. So we've done electron configurations. Let's remind ourselves that we have these subshells, which are the spaces around the nucleus that the electrons occupy, with a maximum of 2 electrons per orbital due to the Pauli exclusion principle, and the Aufbau principle, which says that electrons will occupy orbitals in the order of lowest energy first and then higher energy orbitals. The notation that we're using for these orbitals, and these subshells really, is based on the idea of the quantum numbers, right? The first 3 quantum numbers, n, l, and m sub l. And so we have these types of subshells. So we start filling in this order: 1s, then 2s, 2p, 3s, 3p, then 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, then 5f, 6d, 7p. And so far there is no 8s as far as we know. At least there are no elements that have that orbital or that subshell with any electrons. So we would stop at 7p. That'll get us up to 118 elements right there. Pretty amazing. Okay? So what do we do now? We're going to talk a little bit about the patterns that we see in terms of the periodic table. So what I mean by that is, let's pick an element like potassium. Potassium is element number 19, which means that it has 19 electrons. So I'm going to start by putting in the electrons in the 1s orbital. I know I have 19 electrons, so it's 1s, then 2s, then 2p, then 3s, then 3p, then 4s. And I'm going to stop right there because I know that potassium has 19 electrons, and we won't need to go beyond the 4s. And remember, the s can handle 2, the p can handle 6, because there's 3 orbitals in a p subshell. There's only 1 orbital in an s subshell, so that's 2, 6. And now we're up to 18 electrons, right? You count the superscripts to figure out the number of electrons. So 2 plus 2 plus 6 plus 2 plus 6 is 18. So we've got 1 more. So the 4s has 1 electron. Okay? So that 4s has a spin-up electron, right? But only one. It doesn't have the spin-down electron in it. Okay? Now, it turns out that as you start going through the periodic table, this notation becomes a little bit awkward. It becomes so lengthy, right? Even that right there is pretty lengthy. So what we do is we have a shorthand notation involving noble gases. So let's talk real briefly about the noble gases. The noble gases, helium, right? Which is element number 2. Below that is neon, which is element number 10. Argon, which is element number 18. Krypton, which is 36. Xenon, which is 54. And then radon, which is 86. Okay. These are the elements that are to the far right of the periodic table. So they're sort of the end of the periods, ends of each of those periods. Period 1, 2, 3, 4, 5, and 6. Okay. So here's what we're going to do. We're going to say that if an atom has some number of electrons, let's pick 19, for example, potassium. We're going to choose the noble gas that comes before that element. And the noble gas that comes before element 19 would be element 18, which is argon. And so we're going to write the configuration of this element as potassium, as the same as argon. Argon is the first 18 electrons, and then 4s1. And that would give you the 19th electron. Now look how short that notation is. Look how compact it is, right? There's very little space taken up by that. So it's 18, which is argon. So what we're going to claim is that the electron configuration of potassium is the same as an argon atom. It has the same arrangement of electrons, except it has one extra electron, which is in a 4s orbital. Okay? So now what I'm going to do is I'm going to jump down to a version of the periodic table here. And what we'll do is we'll say, look, here over on the far left is potassium. Look for potassium, element number 19. Potassium, its outermost electron is 4s1. And see how under the symbol for potassium they just show 4s1? What we're going to do is we're going to say that potassium has 18 electrons plus a 19th electron. And the first 18 electrons we're going to call core electrons. And the last electron, the 19th electron, we're going to call a valence electron. And we'll talk more about that later on in the next chapter. But we're going to call these electrons, the ones that have the configuration of the noble gas, we're going to call these core electrons. All of those electrons have a n value, meaning a principal quantum number value, that are less than this electron, right? This electron is in the fourth shell, not first, second, or third, but fourth. So if it's in the fourth shell, we're going to call it a valence electron. So core electrons are the electrons that are in the noble gas configuration preceding the element that you're interested in. And then the valence electron, or electrons, if there's more than one, are the electrons that are outside, beyond that noble gas configuration. So let me show you another example. Let's take one that's beyond krypton. So let's take element number 38. Let's do element 38. 38 is strontium. Okay? So which noble gas is the one that precedes element number 38? Closest to it, but before 38. Be this one, right? 36. 36 is before 38. So we would write this configuration of strontium as krypton. And the way you do that is you use a bracket, square bracket. Remember, we use that for molarity, for concentrations, but we also use it for this. And those would be the core electrons. Turns out chemically they're unreactive. But we still have two more electrons. So how do we figure out what the configuration of those electrons are? We go to the periodic table. If you take a look at the periodic table, strontium is element number 38, right? You've got the first row, the second row, the third row, the fourth row, and strontium is in the fifth row. And then on the left, these first two columns, it would be S1, S2. Let me see if I can, I'll do it here, S1, S2. So 5S1 would be rubidium, 5s2 would be strontium. So you just put 5s2. And there you go. There's our 30. And these would be the valence electrons. Isn't that cool? So S1, S2, this would be D1 all the way through D10. And then this would be P1 all the way through P6. Okay? So if you were gonna pick an element, let's say for example iodine, the noble gas that comes before that is krypton. So you would have bracket krypton. sorry, bracket krypton, I'll do that up here, right? And then you could come over here, 5s2, that would be those two. And then 4d10. Sorry, 4d10s through there. And then 5p5. Okay? And there you go. That would be the configuration of that. Even though we still have quite a bit of notation there, krypton, then 5s, then 4d, then 5p, it's still a lot shorter than it would be if we did all 53 electrons, right? 53 electrons is a lot of electrons. So this would be the configuration of iodine. Krypton, 5s2, 4d10, 5p5. Sometimes people will change the order. They'll put this one before. That's fine if you want to do that. As far as I'm concerned, of course, if you're using online learning platforms, the software may not be as forgiving on that. Sometimes people will do it that way, though. Okay? All right, so there's that. Now, I want to bring your attention to something I just brought up there, which is this idea of blocks. Oops, just lost my little... Okay, so it's convenient to think of the periodic table as having 4 blocks. The S block, the P block, the D block, and the F block. So these are the elements in the periodic table in which their outermost electrons are in those particular subshells. So all the way over at the left, we would call this the S block. All the way over to the right, we call that the P block, sorry. The F block is usually shown separately, like this. It's just sort of broken out as 2 rows, okay? But in this particular picture, they're showing it in the same. The reason that they're broken out as separate rows out of the periodic table is simply that if you left them in, where they're shown in this picture, the periodic table would be so long, it'd be so long lengthwise, that it would be hard to fit it on a piece of paper. You'd have to make the individual squares too small. So they usually just break it out and then slide the D and the P over. It's just a practical issue of editing, okay? So SPDF. So for example, if we take an element like lithium, 1s2, 2s1, that's element number 3, this would be an S block element, because the outermost electron is an S, so it's over here, right? It would actually be one of the 2 elements over here. Whereas if we were talking about carbon, which is element number 6, 1s2, 2s2, 2p2, 2s2, 2p2, sorry, 2p2. The outermost electrons is a P, so that's over here, so we would call that a P block element. So the nonmetals are generally, with the exception of hydrogen, P block elements. The alkaline metals and alkaline earth metals are S block. The rare earth metals, like uranium, those are, or plutonium, those are F block elements. They're called rare earths, lanthanides, actinide elements. And then the transition metals, right, like copper or gold, those elements, zinc, those are in the D block. They're right here. So transition metals are D block. And there you go. Okay, I do want to talk real briefly about an issue having to do with some exceptions to the configurations, to the electron configurations, and it has to do with the transition metals. So there are some electron configuration. What do we call them? Exceptions. And the exceptions I want to draw your attention to are element number 24. And there are some others, but these are the kind of famous ones. 24. 42, molybdenum. And then coming over to Silver, I'm sorry, copper. I don't know why I said silver. Copper is 29. Below that is silver, which is 47. And gold, which is 79. Okay, those 5 elements. Those are all transition metals. These ones are right next to the last row of the transition metals, or last column, I should say. So zinc is number 30. So that's where the transition metals end, that element, in that column. And then these 2 elements right here are in the 4th column of the transition metals. Not of the periodic table, but of the transition metals. And these are these ones right here, and these ones right here. Those 5 are the ones that I want to talk about. So what happens is with chromium, for example, chromium, you would expect it to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. It's the 4th one, 21, 22, 23. So you expect it to be this. And molybdenum, similarly, you would expect it to be 1s2, 2s2, all the way through 5s2, 4d4. But it turns out that these are exceptions. So what happens is called promotion. One electron is promoted from the outermost s to the outermost d. Only one electron, never more than one. So in fact, chromium is 1s2, 4s1, 3d5. 4s1, 3d5. And molybdenum is 1s2, 5s1, 4d5. Sometimes referred to as a half-filled subshell, right? You can fit 10 electrons into a d subshell, but there's 5 in this configuration. So those 2 are exceptions that you should memorize. The other 3, copper, silver, and gold, same phenomenon. The outermost s is promoted to the outermost d. So copper, for example, you would expect it to be 1s2 all the way to, let me write it this way. Erase this. 4s2, 3d9. That's what you would expect. But promotion occurs. Only one. One electron is promoted to the outermost d. So you get 1 and 10. Same thing happens for silver and gold. For silver, that's silver. It goes to 5s1, 4d10. And for gold, it goes to 6s1, 5d10. So promotion for those 5 elements. Those are the exceptions. There are others as well, but those are the ones that are sort of famous. Okay? So practice writing electron configurations. Practice using the noble gas notation, like I talked about up here at the beginning, this noble gas. Practice that as well, and get good at writing electron configurations. Okay?